All right. Good morning, everybody. It looks like it is about 10:01, so we'll go ahead and get started. We were expecting a couple more people, but this session will also be recorded so that you can access it later as well. Let me go ahead and minimize my Zoom here. All right. So welcome to the Getting Started with the Spike Prime Programming in Python. The Spike Prime robot, if you haven't seen them yet, kind of looks like this. The nice thing about this is that it supports the MicroPython framework built in out of the box. So, oops, my ribbon fell out. You could use the tools that are provided by First Lego League to program your robot in Python natively. You don't have to kind of get your own SD card, format it correctly as you do with the EV3s. We'll go ahead and move on to the next slide here that kind of talks about what Python is. So it's a popular programming language that is used for both web development and software development. You can also use it for statistical analysis. I know a lot of college courses use that. You can use it for scripting as well. It does have a simple syntax that closely resembles English. So your students on your First Lego League team should be able to pick it up pretty easily. I would say that it is a step up in difficulty from the blocks-based programming that they might be used to. However, if they switch over to Python, they can use that to not only move on to the first tech challenge and first robotics competition levels of first, but they can also kind of use it in their general computer science classes or other STEM activities that might be taking place in school. It works in a very procedural way, running a single command at a time. So if you notice on the right-hand side, there is an example of what Python looks like. You can see we'll start with line basically 19, and you can see the line numbers right here. And then it will just keep moving down and down and down throughout the program. So I guess we'll take another step back and talk about why even use program or Python in the first place when you have blocks available. There is not many resources available for Python yet, since the Spike Prime and the Python environment are relatively new. And however, it does allow for a greater level of kind of abstraction and the ability to take a step back from the code, write different subroutines that can be reused elsewhere in the program. So you don't have to worry as much about kind of weird blocks-based things not really making sense in terms of variables and allowing the program to change itself on the fly. We're going to go over how to install the programming tools first, which is going to include how to install the Spike Prime software from First Lego League and Lego Education, and then getting familiar with the programming environment as well, since they offer several tools that make programming in Python much easier. First thing you're going to want to do is head over to the Lego Education website. Under the Lego Education Spike Prime section, you'll find the downloads, which are going to be available for Windows 10, macOS, iPads, Androids, and Chromebooks. The only requirement is that it has Bluetooth 4.0 connectivity. I know that if you don't have Bluetooth 4.0, you can usually use a USB cable. However, the nice feature about the Spike Prime is that you can, like the EV3, be able to deploy your programs wirelessly, test them out in real time, and you can actually use a debugging console with the Spike Prime software that allows you to print out what your program is doing, make sure it's working correctly, and things of that general nature. Once you install the software for the first time, you're going to see a kind of blank empty screen that's going to ask you whether you create a new project, access some educational resources. All you have to do is just click on the Home tab, and then you'll select New Project. It looks like I have a chat. Yeah, so you can also buy a USB Bluetooth 4 dongle as well on Amazon if your device doesn't have that. Yeah, thank you for pointing that out. So to see any projects that you have created before, you can click on the My Projects tab that allows you to organize it fairly well. I will say that from my experience, programming in the Python environment is more straightforward than programming in the blocks environment, in that the programs are stored in a single file, which means you don't have to worry about several different kind of components being pieced together in the blocks when you're using My Blocks programs and worrying about separate files being located elsewhere. One thing you have to do as well in the Spike Prime software itself is enable the Python programming in the first place. So to do that, you just have to click on the gear icon and then select Enable Python Programs, which you can see on the right-hand side there. It's going to be under the General section in the Settings area. So when you want to first create your project, you'll go to the home screen, you click on the New Project, and you can select either Word blocks or Python. The nice thing about this is that if you want to have kind of two different teams working on two different styles of programs at the same time, you can. If you use Python, you were not exclusively limited to using Python on your robot. You can still use the block space format if you have some students that are more comfortable in that. If you have other students that want to try out the Python, they can create their projects and they can be working on it simultaneously as well. First thing you're going to need to do as well, once you have your program set up, is connect to your hub in the first place. So you'll click on the connect button, which is going to be a little block in the upper left-hand corner of the programming suite. Then you'll choose which option you will program the robot with, either USB or Bluetooth. If you're using Bluetooth, there is a Bluetooth pairing icon on the robot itself, which is going to be right up here in the upper left-hand corner. When you turn on the robot, you'll see the home button right here lights up. And then once it does its beeps like that, what you have to do is hold down the Bluetooth button until it starts blinking blue. One thing to note is that if this is your first time connecting to it, in a while, it might ask you to do a firmware update. You can only do that through USB. So you do have to have a USB connected device in order to do that. Have not tested it on a tablet. So not sure if it will still require you to do a firmware update with the cable. If you're using kind of an iPad or Android tablet. So that's just something to keep in mind. You might have to update the firmware for the first time once you connect it. One issue I noticed on my Windows 10 device is that I would have to manually go into the Windows 10 settings to confirm the pairing for the first time. Otherwise, the app itself wouldn't ever connect to the hub. It would just sit there saying that it's trying to connect. Really nice thing you can do is view all of the different sensors and where they're plugged in real time. This is similar to the EV3 software, but in my opinion, this one makes it a lot more visual so that you can record things much easier, as well as changing what the actual view of the sensor is. So for example, with the color sensor, we're not limited to just seeing the color output. We can also see what the reflective light is in real time as well. So this is going to be after you've paired your hub, you can go into the hub dashboard, and then you'll see what all of the different motors and sensors are plugged into each port respectively. You can also manage your programs directly from here as well, and your data, so that if you want to, for example, log all of the kind of readings from the robot to a text file, you can do that as well from the Python framework. You can also kind of pull files, I believe, from the dashboard as well if you want to take a backup of them. So to actually run your program, when you are in the programming environment, you'll notice in the bottom right-hand corner, there's going to be a play icon, a stop icon, and then you'll see kind of the numbering system. If this is your first time ever looking at the SpikePrime, instead of naming your files individually, because this doesn't actually have a display, what you do is instead there's left and right buttons on the robot itself that allow you to select kind of the slot or index of the program itself. So for example, if I save a program to index 0, I can recall it from here. As well, I can go all the way up to index 19, I believe, on this. So you can have up to 20 programs stored on this at once. So to actually start running your program, all you have to do is click the play icon. This will start from whatever the currently selected file is. You can also choose to stop it if you're running it in real time. That way you don't run into any weird issues where the program might start crashing into a wall. You can also choose which slot you want to download the program to using the kind of screen that you can see there. So the console here is going to allow you to view information from the robot. So if you're running your program in real time, you can use print statements, which we'll talk about a little bit later, to kind of view data coming from the robot in real time. The nice thing about this is that you can format it exactly as you want it to be seen. So if you are, for example, trying to calculate something in an algorithm, you can print the results to the console to see the result of the algorithm in real time. I know that when I was doing some of the debugging, what I would do is for the turning algorithm to help it follow a line, I would print out what the turning adjustment was so that I could make sure it's trying to turn in the correct direction instead of veering off in the wrong way. These do have to be directly implemented by the programmer as well. So this one's not going to be included by default, kind of like reading out the sensors in the hub dashboard. You do have to manually explicitly say that you want to print to the console as well. And it looks like my image of what the console is, it's not loading, but we'll see a couple more examples throughout this presentation as well. Really nice thing about this is that it has a knowledge base built into the software directly. So that's going to be located on the right-hand side of the programming environment. It's going to be a little kind of double bar line on the Windows 10 environment. That's going to be a drawer that you basically have to pull out, and then you'll see the knowledge base, which includes all of the different kind of Python functions that are available. It includes coding examples, what all the different parameters that you need to supply are. So it's really useful for being able to look up how to do something. You don't have to go to the internet to search it up, for example. So once you click and drag it out, you can just go through all the different things that it has available. And it does not include information about how to program in Python directly. It's only about the functions that are available kind of in the Spike Prime flavor of Python, if you will. So if you're more curious about, for example, how for loops work, you will have to go to the internet for that, or while loops, assigning variables. This one is just going to show you how to create all the different parts of the robot, which we'll go into more detail later. All right, and that later is going to be now. We're going to transition into how to write your own programs. That's going to be everything from how to create your first program to the spacing and indentation of Python, how to move motors, how to read sensors, how to use conditional and loops, which allows your program to change its behavior on the fly. Also defining functions so that you can reuse code in several places, and then how to handle errors. So to create your first program, when you create your project for the first time, it'll already be populated with everything that you see on this screen here. So just to quickly recap, if you're not familiar with Python, what all these different lines are, on lines 1 and 2, which again, you can see the line numbers right here, those are going to be your imports on lines 1 and 2. That's going to include the libraries on how to actually use the light matrix, how to use the button, as well as how to use the HUD, all the different sensors. Line 2 is going to have the spike control, which allows you to kind of avoid some of the Python syntax and directly input your wait loops into the spike program and utilize the onboard timing system as well. So one thing to keep in mind is that you really should try to keep those lines. That way you don't have to worry about later manually adding the imports when you start trying to type out your code. I know that this one does not have kind of the nice IntelliSense auto completion features that most integrated development environments have. So I would recommend just go ahead and leaving those in there. And line 1 is going to be really long as well. That is normal. So thinking about libraries, one way to consider them is similar to the EV3 MyBlocks. So those are kind of a level of abstraction where you just have to supply the parameters, right? But what's different about the libraries in Python is that you do not have to manually define them. So these are going to be the blocks that are included by default. Line 4, you can see that we have the line hub equals prime hub with parentheses. That is going to declare your hub itself in the programming suite so that you can interface with some of the things that are built directly into the hub, like the light matrix that you can see on line 6. So because you don't have a display, you do have to use the light matrix with the robot turned off, but you can directly put data on the screen, I guess the pixels that show up right here as well. So the happy right there that you can see is going to show happy face. And I do believe you can also just individually index the pixels on the display as well. So I guess we'll take a quick second here to ask if you have any questions on anything that we've covered so far before we move into the more kind of nitty-gritty details of Python and how to create your program. And feel free to unmute yourself or just type something in the chat as well. Sweet. Well, I don't see any questions, so we'll go ahead and move on then. One thing to keep in mind about Python, it is very specific about how it wants its spacing and indentation. So if you're familiar with any other programming languages like C or Java, those ones you can generally put spaces, new line breaks, indentation wherever you want, and the program will automatically be able to figure out what you mean. Python uses those spaces, indentations, and new lines to kind of specify where new lines start, where different code blocks end. So new instructions to the robot are indicated with a new line, meaning that the expressions you write out cannot be broken up onto multiple lines. You can see an example of that here on the right-hand side. The first line, line 19, that assigns the turn amount variable, the sensor value plus 5 divided by 3 is correct, but lines 20 and 21 are incorrect because the divide by 3 is on a new line, meaning that it will run turn amount equals sensor value plus 5, assign that into turn amount, which we'll go over variables a little bit more later. And then it's going to try to run the divide by 3. It has no idea what to divide by 3, so it'll print out an error saying, I believe, operand unfound. Indenting a new line indicates that it is part of a new code block, such as a function, if statement, or loop, meaning that when you decrease the indent, that means that it's the end of that code block. And we'll go into more loops later, but just know on the right-hand side, you see the while loop there, and then there's the colon. The new line after that is indented, which is going to start the motors at a specific power. And then once the while loop is over, then it's going to decrease the indent to let the Python interpreter know that it does not need to continue running it, and instead it can just run the line motors.stop and continue on from there. Writing comments are especially useful for explaining not only what your program does to the programmers themselves, but also the judges. So when you're writing your comments, you generally want to keep them more specific about what the program itself is doing, rather than just describing or elucidating what that line says. So basically more, you want to use your comments for what the program means rather than what the program says. So for example, there you can see I have line 34, which is going to be while true. Above that, I have the comment saying that that's just my main loop for the program. And then we'll go into more about the different types of comments later. But you can see there, line 35 as well, I have calculate the turn amount based on the reflected light value. And then also I have a line that says move the motors at 50% power and the specified turning amount. And also kind of what that line does, saying it drives without a set distance so that it does not jerk while moving. The judges, when you show them these code reviews, are going to be especially happy if they do describe what the meaning is. I typically like to see, when I'm doing robot judging, about a 50% of the code, 50% of the comments. That tells me that the programmers are confident enough in the code that they not only know what it's doing, but they can also share it effectively with other people as well. So there's two different types of comments that you can actually write out here. You can do single line comments, which are prefixed with the pound symbol. Those are going to be highlighted in green in the programming environment. And then we'll also have multi-line comments, which are going to be in the triple tick marks there, that allow you to just keep typing until it hits the end of the triple tick marks. One thing I've seen teams get a little confused with, especially the newer members, is that if you have the triple tick marks and you never end the triple tick marks, it's never going to end the comment and none of their code is going to run, right? So that's something to keep in mind of, is just keeping track of the highlighting, making sure that what is highlighted in pink doesn't actually need to be run. So real quick, the comments will not be interpreted by the robot at all. They are actually removed during the processing phase. So that's why you can kind of type anything in there as well. Additionally, if you're working on code and you're not sure if it's going to work, you can comment it out to test different parts of the code first, and then add the comments in there step by step. So one debugging trick that I like to help my students with is you start with basically the entire program, right? Or you can do it piece by piece, but let's say they were zealous and started with the entire program. What I encourage them to do when it doesn't work is comment out everything but the first line, see if that works. And then if it doesn't, fix that line, And then after they know that line works, they uncomment the next line after that. That way they're going and testing each piece of the code in a stepwise fashion, and they're less worried about figuring out kind of, oh, in their head, where is the program no longer working? Instead, they have a definitive answer right there in front of them, which helps them keep on track. So to create variables, all you have to do is put the name of the variable on the left-hand side, followed by the equal sign and an expression. You refer to a variable by typing its name. So on the right-hand side, you can see a couple of different examples of what that means. We have a number, which is going to be equal to negative 15.674. Because we are programming in Python, remember that we don't have to worry about declaring the variable type like you might have to in Java or C. You can just go ahead and type the variable name, and the Python interpreter will figure out the rest for you as well. Number types support positive numbers, negative numbers, 0. You can do decimals in there as well. All of that will be handled automatically for you, so you don't have to worry about any implicit or explicit casting as well. You can just type in the number, and you know that that's what's going to be assigned. One thing to note is that if they put spaces in between, that might break up the number as well, and the Python interpreter won't know what to do with that. So just make sure you keep it all kind of squished together without any spaces in there as well. On the next line, you can see that we have a string type that is going to be equal to hello. So to indicate a string, you can either use quote marks or the single tick marks. Either or will be handled correctly. And the difference between a raw number and a string is that a string is going to be reserved for text, whereas a number cannot include any text in it whatsoever. So when you do the string, if you put a number inside your string, it's going to be treated a little bit differently than if it was just a raw number. So one thing to keep in mind is that if your students accidentally put a number inside of a string, they might need to kind of get it out of the string in the first place using explicit casting to get it into the number data type if something's not working correctly. The other data type that we're going to cover today is going to be Booleans, which can either be true or false. Those are especially useful for kind of conditional loops, that while loops, kind of determining when something needs to run and when something does not need to run. So yeah, strings you're also going to use for identifying parameters and printing the console. So that's kind of when they're useful for, is when you're printing data to the console. I personally have not used strings much in my program, except just for printing out data. So I wouldn't be expecting too much of that. Lines 12 through 16, you can kind of see what different variable assignments do. So we have number 2, which is going to be equal to number plus 20. So number is going to go ahead and retrieve that variable, which is going to be negative 15.674, and then we'll add 20 to that and store it in number 2. The original value of number will not be modified when you make this modification. So for example, if I set number to negative 10 on the next line, that's not going to affect number 2. If I want to update number 2, I have to rerun the line number 2 equals number plus 20 to reflect the change of number. So that's one thing to keep in mind, is that because this works in a procedural way, it will run one line after the next, and anything that happened in the previous line, if that was not stored, it will not consider it anymore. String 2 equals string plus another string. That is going to be known as string concatenation, which allows you to put two strings together. So you can see above that in the comment, string 2 is going to be equal to hello world at that point. One thing to note is that all of the different operations that are available on numbers aren't necessarily available on strings. So if we have a number, we can add, subtract, multiply, divide, do exponents with, we can do square roots with it. You can do, as well as calculating the remainder. So it's all going to be available with numbers, but with strings, it might not be. So one thing I've seen kind of the students try to do is to subtract a string from itself, which typically results in some weird behaviors. And then down there, you can just see an example of Boolean equals false. So Boolean's kind of more specific. They really are just true or false. All right, so write data to the console. You're going to use a command called print. So you'll notice that whatever you want to print to the console, you'll first type in print, and then you'll do parentheses. So when we use parentheses, we have to make sure that they are matched correctly. So if we have parentheses on the left, we have to have a closing parentheses on the right. And then whatever is in between is what we're going to pass or supply to the print command itself. So in there, you can see I have a new string, which is going to be color input, and you'll see those weird curly braces there. That is going to allow me to supply variables into those positions. So after the string is done, you can see I have my opening tick mark, my closing tick mark. I have a dot there, which is going to allow me to access different string functions. And then I'm going to type in format, and inside of there, I can do the different variables. That is one method that you can do. The other method is you can just do string concatenation, convert your variables into strings, and then just add the two strings together. So that's the second example on line 46. I would recommend using 46 more because it is easier for the students to understand what's happening there because they're just adding versus doing function calls, which they might not be as comfortable with yet. So the formatting does allow you for more complex functions when you're printing out those, such as truncating the length of a number or passing multiple numbers kind of simultaneously using the substitution method there. The print statement as well supports putting variables, strings, and expressions into there. So if you just want to print the output of a variable without having to type in the string, you just have to supply the variable name, such as color amount or turn amount in this case. You don't have to worry about doing any weird string concatenation things. So now we're going to move into some of the more specifics about how to interface with the SpikePrime itself. If you recall back to the EV3 block-based programming or the SpikePrime block-based programming as well, there are two different types of motors that you can interface with. Those are going to be single motors and motor pairs. So if you look on the robot that I have here, the motor pairs are going to be the drivetrain, for example. And then I also have a single motor located here on the front. I would just type in it as a single motor. I wouldn't try to pair that with another motor as well. So the motor pairs are especially useful because they give them different functions that they can use for not only controlling the individual speeds of the motors kind of synchronously, they can also directly interface with the turning amount on the wheels instead. So they don't have to worry about trying to calculate, oh, I need to have this differential on the drivetrain in order to make it turn this amount. They can just say, go at a speed of 50% and then turn left or right this amount from negative 100 to 100. So on the right-hand side, you can see how the motors themselves are declared. So you would type in your variable name, and that's going to be equal to motor pair. In the parentheses, which are going to be known as the parameters, we're going to put the two different motor channels that we have in there. So the SpikePrime no longer uses the 1, 2, 3, 4 ABCD numbering system. This one only has 6 channels, and it gives you A, B, C, D, E, F to plug in anything on those. The nice thing about that is you are no longer limited to having a maximum of 4 sensors or a maximum of 4 motors. You can have up to 6 sensors and up to 6 motors, I believe, plugged into this at a time. And also the gyro is integrated into the SpikePrime hub by default now. You don't have to worry about plugging that in externally, which saves you a slot as well. And we'll go over more of the sensors later. So if we want to declare a motor pair, you just have to type in motor pair, parentheses, the 2 motors. The left parameter, in this case F, is going to be the left motor. B is going to be the right motor. So one thing I like to have the students do, just to make sure that they declared their variable correctly, is try to move the motor at 100% speed, see if it moves forward according to what they think forward is. If it doesn't, then they need to swap where the position of the 2 variables are. That way, it moves in the direction that they're expecting. So if you just want to declare a single motor, you just type in your variable name equals, and then just motor without the pair, and then you only supply it the first parameter. So if you want to forcefully stop the motors, all you have to do is type in motors.stop. One thing to keep in mind is that if you are supplying the speed of motors, telling them kind of how fast to move, you want to make sure that you call stop at some point. Otherwise, if you don't give them a new speed ever, they're just going to continue on with that speed. So that's something that I've noticed my students doing, is that when they try to move the motors using just a set speed, once their loop or function is done, then the robot will just continue on driving at that same speed, never stopping. So after the loop, they have to type in stop, which is, I believe, an example. Yeah, on this line, you can see how after the while loop is completed, they do have to type in stop. There we go. So now a couple of the different functions that are available. You can move motors by degrees, rotations, seconds, inches, or centimeters. So all you have to do is just type in motors.move for your motor pair, or whatever your variable name is there. So that does bring up a good point. Right here is where you're going to supply the variable name. Sometimes they try to type in the motor pair here. That's not entirely correct. They really should be assigning the motor to a variable first, and then you would access the variable, put a dot after it, and then supply it with the function that you're trying to do. Oops. So in this case, my variable is called motors, so they need to use the variable motors dot to access its different functions. So we have the move there. We just tell it the amount, the units, the steering, and the speed for the move. So for example, if I wanted to just move one rotation straight in a line at 100% speed, I would just do 1. Then I would give it a string telling it to do rotations. And then I would do the steering amount as 0. So just remember that steering goes from -100, meaning it's biased counterclockwise. Yeah, versus 100, which means it's biased towards the clockwise direction, according to whichever direction they set us in front. And then you have the speed there, so you can supply that with a positive number to go forward, or a negative number to go backwards. One thing to keep in mind is that you don't have to worry about truncating your variables. So if I try to give it a speed of, let's say, 3,000, it'll just go ahead and truncate that to 100, and I don't have to worry about going out of bounds with this. So another example is if they want to move by inches and centimeters. That's something we always encourage them to do, so that they can just get a measuring tape and physically measure out on the field how far they want to go. To do that, you have to define whatever the number of inches traveled or centimeters traveled per rotation is. You don't have to manually do the conversion using the circumference of the wheel times 2 pi r. I think, no, pi r squared, that's circumference. So all you have to do is basically set this to go 1 rotation forward using the motor.move command. And then you would go ahead and just measure out with a measuring tape how far did it drive during that 1 rotation, and plug that in there. So then what you can do is say motors.move however many inches or centimeters you want it to move, tell it that you're moving in inches or centimeters, and continue on from there. So that should be everything with motors. There is more available to motors that you can experiment with. One thing to keep in mind is that if you want to use any of the advanced functions, such as reading what the actual encoder position of a wheel is, you can't do that in a motor pair. You have to have a single motor declared in order to do that. You can double declare your motors though. So for example, you'll notice I have on the bottom line, motors equals motor pair F and B. I can declare another variable called motor encoder that I can get the motor encoder variable from, and I can just declare that as F as well. So it's okay that I have motor declared in 2 different places, but one thing to keep in mind is that if you are trying to use both motors and motor encoder to set the speed, sometimes the values can fight with each other, and whichever one you call last is the one that's going to win. Also, you can see some weird behavior with the motor. Let's say I put it in a loop telling a motor pair to run and then a single motor to run. If I have the same motor being called twice in rapid succession like that, that can cause the motor to freak out, and then the students get very confused and they won't know what to do from there. So just try to avoid kind of using different motor variables for setting the speed of a single motor. All right, this is going to be an example of how you can read all the different sensors that are available. The 4 primary ones that you have are the color sensor, which is also a reflected light sensor. We have the distance or ultrasonic sensor, which allows it to tell how far away it is from something. we have the force or touch sensor, which the cool thing about the touch sensor on the Spike Prime is that it is not a simple push telling you that it was just pressed. You can actually read how hard it was pressed. Not sure how useful that would be in terms of first likely robotic applications, but that could lead to some interesting creations by the students. And then you also have the motion sensor, which is basically your 6-axis, I believe, accelerometer and gyro. So that allows you to tell kind of which direction is it moving towards, as well as is the kind of angle moving itself. So for example, if I'm turning the robot in this direction, I can use the gyro sensor to tell that I'm moving in that direction itself. Again, the motion sensor is integrated into the hub now. You don't have to attach it externally. You just have to use the hub function itself. The sensors are especially useful if you are doing control loops. So for example, if you are trying to follow a line, what you want to do is declare a new color sensor, get the amount of reflected light it sees, and then you can do a, while the reflected light is greater than a certain amount, turn left, otherwise turn right. So on the right-hand side, you can see examples of how to declare those 4 sensors. Again, there are more sensors available, especially like the light matrix is one that you can interface with. Those you can just refer to the programming manual for more information on. And the things declared here are not exclusively what you can use the sensors for. Those are just the most common uses that I found that the students need to actually use. So there are more things available if you go to the knowledge-based or reference manual in the program. Okay. So starting with the first one, first thing we have to do for the color sensor is declare its variable. Variable is what they're going to use to access it later, which is going to be equal to the color sensor. And in the parentheses, they put the port it is attached to. Remember, if they don't physically have access to the robot, they can always just put in a temporary variable there. The nice thing about setting it as a variable is that you can change it later in the program in case something is wired differently. You can also view all of the different ports from the kind of hub management interface in the programming environment as well. They just need to remember which port it's plugged into. For example, on this robot, the wires are a neat tucked spaghetti mess, and there is absolutely no hope of tracing the wires to figure out where they're plugged into. So I would definitely recommend just using the programming environment to figure out where everything is plugged in. But anyways, for the color sensor, you can do color.getColor, which will return either a string containing red, green, blue, a couple of the other different colors that it can see. The full list is available in the knowledge base. And then you can use the color value to determine different things. So if you're not just following a line on the field, for example, you can wait until it reads kind of a magenta color. For some of the specific colors, what you might have to do is actually get the red, green, blue values directly instead of just saying get color. That way they can do a threshold on it to say, is there more red than blue? If yes, then chances are it's a magenta color. You can also just get the amount of reflected light underneath it as well, if you just want to follow a black and white line. For the distance sensor, same thing, you kind of have to declare your variable first, which is going to be equal to the distance sensor, and then whichever port it's plugged into. And then to get the distance in inches or centimeters that it is away from something, you just call the variable that you made dot get distance in inches or centimeters. One thing to keep in mind is that that is going to be the value that is directly in front of the ultrasonic sensor. So on the Spike Prime, you can see that is located here. If I have my hand in front of here, it can still read this value. But if I have my hand out in front of here, it can't read the value because the ultrasonic sensor isn't located on the side. So that's something to keep in mind. You can't use the ultrasonic sensor to follow a wall as well. That's a really good use for it. So you can say, while the distance is in this range, we know we're going straight. And then once it exceeds this range, we need to turn a little bit to keep it going in a straight line. So that's the advantage of having it on the side like this as well. For the force sensor, again, you just have to declare your variable, set it equal to the force sensor and then the port, and then you can get whether or not it is pressed, which is going to return a Boolean value. And then you can also get the amount of force that is being pressed with as well with that second function that you can see there. The motion sensor, because it is built into the hub, it is not going to be a separate function call like the force equals force sensor. First, you have your hub variable declared. You already have it declared in the default program. You don't have to worry about typing it out again. But then you would call hub.motion underscore sensor, which is the motion sensor integrated into the hub, and then dot get yaw angle, which is going to be, depending on the hub orientation, if it's flat like this with the screen pointing up, it's just going to be kind of the heading that it's pointed into, which is wrapping from -180 to 180. You can also reset the yaw angle, which will allow you to zero it. So for example, my students have a drive straight program that they can use, which they first thing do is reset the gyro angle so that it's pointing at 0, and then they just tell it to move in a straight line. And then if they see it deviating from 0 at all, they know they need to either turn left or right appropriately. And I believe an example of that program is also included in this presentation if you want to check it out. And then we also have a couple of programming examples for Python on the Arizona First LEGO League website. All right, moving into while loops. These allow your code to run a certain set of methods or blocks or functions until a specific condition is no longer true. So line 94 that you can see there is going to be your general declaration for a while loop. So you would type in while, give it parentheses. Inside the parentheses is the expression that you're checking for. So expressions, conditional expressions specifically, need to evaluate to true or false. So on line 85, you can see an example of this. We're going to use ultrasonic.getDistance is greater than 40. So the greater than 40 is going to kind of result into a true or false condition, which the while loop checks. So you can't just give it a number. You have to compare it to something else, or just give it a raw Boolean value like a while true loop, which will cause it to run indefinitely until you break from it. So you can see at the end of the parentheses in the while loop, we have to put a colon, and then the next line, we're going to indent it, telling it that this is part of the while loop. So you can see there, line 85 through 92, that's going to print that it is trying to drive forward. On the next line, it's going to start the motors at a power. So that's another function that you have available. That basically starts the motors at 50% and doesn't care how far it goes. It just cares that the motors are started at 50%. That's really useful for control loops where you don't want that kind of stuttering behavior. I know the first iterations of First LEGO League, most of the loops, what they did is they kind of inched forward, checked the amount of light that they saw, inched forward again, checked it, turned a little bit, and then just kept inching that way. But by starting it at a power, you can have a nice smooth kind of line because the speed will be adjusted at a much quicker rate. So then you can see we have an if statement, which we'll get into a little more later. That is just going to check a condition once and then run it if it is true. So if the amount of reflected light ever gets less than 20, then we'll break. So the break will tell it to forcefully end the while loop, regardless of whatever the ultrasonic value is in this case. So you'll notice that the if loop has another indentation telling it that it's part of that if loop. And then when the loop is done, we just have to go back to the original kind of vertical column that the while loop is on. And that's going to be the line for when the while loop ends. So yep, that's basically everything there is to this. Line 70 through 73, you can see the basic while true loop that will run until break is called. And you can see a couple of examples in there of what you can do in your main loop. So one thing that I like to encourage the programmers always to do is to have their main while loop that they're going to use. Otherwise, their program will only run once and it will never end. I guess, yeah, that does bring up a good point. Try to avoid using while true loops because that means that the program is going to run indefinitely. So for example, if you're going out onto the field, you're trying to do a single mission, if you're in a while true loop, when it gets back to base, it's going to do the exact same thing again. So try to avoid using those, but for testing purposes, I like to use those to make sure that, for example, the drive straight algorithm is working. So that should be everything for while loops. Now we'll go on to for loops. I haven't seen my programmers come up with uses for this as much. The for loops more specifically allow you to just go through a certain range of numbers, assigning that to a variable so that you can actually read it. So the difference between running a while loop and a for loop is that a for loop is if you know a set number of times that it's going to run, whereas a while loop will tell it to run indefinitely until a condition is no longer true. So on the right-hand side, you can see you start off with a for, and then you want to declare the variable that you're actually going to be using inside of your loop. So an example of that is we'll say, for every single number inside the range 1 to 100, just print the variable. You can make sure, again, the print x line is on a new line, and it's going to be indented, indicating that it's part of the for loop. That way, it'll go through assigning x as 1, it'll print it, it'll go back to the for loop, it'll increment x to be 2, it'll print 2, and then it will keep doing that until x is 100, and then once it is 100, it'll no longer run, and it'll print all done. So that's going to be the range start finish function to declare how many times it should run. If you have a list, which is slightly outside the scope of this, you can just go ahead and just pass it the list, and it'll assign the variable automatically. So for example, on lines 94 and 99, I have a list colors, which is just going to be equal to red, blue, green. And then for every single kind of variable stored inside that list, I'm just going to go ahead and print that variable. All right, moving on to how to define your own functions. Functions allow you to reuse specific parts of your code multiple times. So these are also known as methods in different programming languages, but they just allow you to execute a specific block of code when called. So if you only need something to run kind of, I guess, once, and it doesn't need to go in a while loop, you can define a function for it. So for example, on the right-hand side, I have a function declared as scale, and that's basically a y equals mx plus b function that just allows for kind of scaling a value to a certain range. So for example, I might have my light sensor values coming in. I can declare what my white value is, what my black value is, and then I can scale that to a certain output range. So for example, if it's on the white line, I might want it to turn left, and I would set that up here. It's on the right-hand side, I'd want it to turn right, and then I can just pass whatever the x is and then get a y. The nice thing about this is that it can take in parameters as well. So when we see def defining a new function, then we can give it the function name, which in this case it's called scale. In the parentheses is where we put the parameters, which allows us to change the function on the fly, depending on how we're calling it. So again, we use a colon, and then we go ahead and just declare everything in there. Let's see. Yeah, okay, that's right. So yeah, we'll do the parentheses, put the colon there, and then we assign the values in there, and you can notice the amount that's going to be the variable being referred to, and then we would say return a certain amount of data. So the return function is when the program will end that function call, and that allows you to kind of get data outside of the method as well. So it returns data to the caller, which is especially useful for assigning variables. So in this case, what I could do is I could say, have a variable declared as my scale amount, and that's going to be equal to scale. In the parentheses, I could supply that with the gyro. I could supply that with the light sensor value, which is what I am doing in this case. And then depending on what that amount is, I can return a specific amount of data. In the example here as well, you can see that I have low light, high light, negative turn max. Those are all declared outside of the function itself. That I just have located at the top of the program, which allows them to change those values on the fly to see if they want to use different turn amounts or a different line amount in case the function no longer works and they need to tweak it a little bit. You could also do those as parameters, but in that case, just have them as global variables. One thing to note that I didn't talk about during the variables section is going to be a variable scope. So you'll notice here we have the variable inmin, inmax declared inside of a function, meaning it is only accessible inside that function. As soon as I call that return line, those variables are gone for all intents and purposes. You cannot access them anymore. So just keep that in mind. Sometimes what my students especially do is they declare a variable somewhere, and then they will overwrite it every single time with a new value. if they're in a while loop, or what they might do is find it somewhere where it's outside the scope, they can't read it anymore, and they just need to move the variable to somewhere else where they can actually access it. Now we're going to talk about how to actually handle errors. So in the event that something is completely wrong and the Python interpreter catches that, it's going to show the error in the console that prevents it from continuing to run. So these types of errors will forcefully stop the program. They cannot continue after that. They cannot recover unless you fix them. It'll show the stack trace, which is the line number and function of the error. Common errors include the variable not being defined, or it can't convert from two different data types. So on the right-hand side here, you can see the first one I have is going to be the type error, can't convert a floating point number to an integer. Floating point numbers are numbers that have decimals. Integers do not have decimals. So I have to explicitly tell it how to convert from a float to an int. You can usually just look up an example of how to do that. But you'll notice here, the bottom line will always be the type of error that it is, and it will give you a little description of it. And then here is going to be your traceback, which will tell you where to find it. So when it says the programmer, you can usually ignore that because that's going to be what is provided by Lego and their programming stuff behind the scenes. And then you can see the project here. So we called line 38, which went to another function called drive straight, which is going to be located on line 17. So typically the bottom one is going to be the most specific kind of stack trace error telling you where to go back in your program. If we look at the next example here, this is a name error where this specific function isn't defined. So what I have to do is line 34 is where it's trying to call that function. I would go there and I would say, okay, do I need to create this function, or do I just need to change the name to resolve to something that actually exists? Name errors typically work on functions and variables as well. So if they try to refer to a variable that doesn't exist, it'll say variable not found and print out that error. And these are going to be printed to the console, just keep that in mind, which is going to be located at the bottom of the programming environment. Here's a sample program that I just created. It's going to allow the robot to drive straight using the gyroscope, I believe. Yep. So it uses the motion sensors gyroscope to check that. So at the top, you can see we have the hub equals the prime hub, the motors equals the motor pair, and then the motor encoder, which is going to be whatever the motor that I have to read the encoder from, since the encoders are not available from a motor pair. Here I just have a big function that declares the drive straight, and I can provide it the number of rotations that I actually want it to drive straight with. Then I can convert the rotations into degrees to supply the amount of distance. And then what I do is I get the original angle that the robot was headed towards. The other option is to just set it to 0, but in this case, setting it to the original angle allows the program to kind of still keep whatever its angle was throughout the field, and instead just refer to the kind of delta between the original angle and whatever the new angle is. So you can also see there, we get the original position of the motor encoder, and we have a while loop set up there, which is going to check while the original position minus the degrees counted on the motor is less than the distance. So one downside of this is that it's only keeping track of how far one motor has traveled. It cannot keep track of how far both motors have traveled. And then as it needs to do slight adjustments in keeping it straight, this is going to slightly vary. I've noticed that typically it's within a couple of degrees of however many rotations you plugged in, but you might have to do some more fine tweaking to get it specifically there. So inside the while loop, you can see we calculate what the new angle is, which is going to just get the angle as it moves. And the delta is going to be whatever the new angle is minus the original angle. And then I scale the difference, which means for every 1 degree off, I'll adjust the turning by 2. Looks like my comment I never updated. So the times equals there just means delta equals delta times 2. Something to keep in mind. And then it will move the motors by the step distance, and the speed is proportional to the delta. So I have the step distance just set to a constant 50. Actually, I think that's an old comment. So when I first wrote this program, I was doing kind of the jerking movement where I wasn't using just the speed is actually telling it to move a set distance, check it again, and then turn a little bit. But the new version kind of uses the speed to change it. So this would be 50 minus delta, 50 plus delta. That'll create a differential on the motors. So if the difference in the angle is 0, it won't turn at all. But as the distance or the delta between the two angles grows, it'll turn left or right appropriately using this. So obviously I don't give the students that I work with this program directly. I typically like them to kind of identify first the problem and then walk them through kind of, okay, so we have this problem. What's the very first thing we need to do? What sensors are we going to use? What motors are we going to use? Declare that, get a basic shell for it, and then avoid programming it altogether and just write out kind of what the different functions that we need are, and then how we're going to calculate that and plug them into the program in order to do this. That way it develops their critical thinking skills and they can work on the programs themselves. And then the satisfaction that they see after they get the program working is always incredibly satisfying as well. So yeah, I just have these programs as kind of like my own little reference to make sure, like, kind of in the future, if I'm helping another person or another team, kind of what the basic outline should look like. So you can see here, after the while loop is done, I tell the motors to stop. Otherwise, once the program is done, it'll just continue on driving at that speed. And then here, I actually have the function call, which that should not be a 2. That'll actually result in an error. It should just be drive straight. And then I give it the distance and rotations that I actually want it to move. And I believe that is the end of the presentation. There's about 2 minutes left until it's officially over. So if you have any questions, you can go ahead and ask. I guess I never even introduced myself in the first place. So my name is Zach. I am one of Laura Grosso, the program delivery partner for First LEGO League in Arizona's student workers. I have originally participated on a First LEGO team back when I was still really young. And then I graduated from First, and now I do First LEGO League as a way to give back. So it looks like something came into the chat. Programming manuals. So those here, actually, I think I have the environment. Yeah, so let me share the screen real quick. I have the Spike Prime software here, so I can go into a program. The left-hand side here is going to be the knowledge base. So all I have to do is just click on this little icon here that pops up with the knowledge base. And then I can click on all of the different kind of functions that are built in. So the force sensor, distance sensor, color sensor, gives me examples on how to use them. And then all the different functions that are available in there as well. Does that answer your question? Pull the chat as well. Sweet. Well, if there's no other questions, then I'll go ahead and end the presentation here. Thank you so much. If you have any other questions in the future, I would definitely recommend reaching out to some other teams. You can also reach out to arizonafll@asu.edu. I have access to that inbox, and I can go ahead and help you out for there. So thank you. Good luck with your season, and have a great day while I figure out to end the Zoom. Let's see.
Jack, are you still there?
Oh, yeah. Whoops, my audio is really low.
All right, a question for you. You mentioned there were some programming examples on ASU's site.
Yes.
How would you go about finding those?
Let me go ahead and pull up the website real quick. Let's see. Okay, so here's the Arizona First LEGO League website. So we'll just go ahead and go to the, I believe I put it under robot game. Yeah, so sample code here. I have the proportional line follower already plugged in there. I'll go ahead and include the heading program that I made as well, but in here you can just see all the different lines in here. So you can copy and paste this and plug them into your program.
So under ASU, the robot games?
Yeah, so you'll start at the outreach.engineering.asu.edu,
Yes.
and then you can go to the First LEGO League Challenge section here, and then under Robot Game.
All right, thank you.
Yeah, thank you.
Thank you for the presentation. I appreciate this one, and I watched one a couple weeks ago on the EV3.
Oh,
This is
nice.
This is our first year, so we're figuring things out, so I figured we would just leap into the new vehicle and start out with Prime. And I got
Oh yeah.
mostly young individuals, but I think by the end of the year we'll be ready to play with the Python as well.
Nice. Yeah. I would definitely
Under 10
recommend.
year-olds.
Oh yeah. Starting out with the blocks gets them familiar with what the robot actually is in the first place. And then once they're familiar with all the different terminology, then they can switch over to the Python and the more advanced stuff. So yeah.
Could you export the word blocks as a Python program?
Ooh. Let me see real quick. I know for first tech challenge we can, but I have not tested it with this. Let me see. Not that I can see, no. So you would have to retype it directly from all the lines.
All right.
Yeah.
Thank you for your time.
Yeah, thank you.
You have a good weekend.
Yeah, you too. Thanks.
Thanks, Zach.
Thank you. How do I end a Zoom meeting? Let's see. So yeah, we'll also have a recording of this available on the website as well, the first LEGO League one. So I'll go ahead and stop the recording here.